As data analysts, our primary job is to look at a chaotic, random world and figure out if there's actually an underlying pattern. That search usually leads us to statistical software, which spits out outputs that look entirely unrelated. You might be checking the prerequisite for a Welch's t-test in Python, reviewing an analysis of variance table in Excel, or evaluating an ordinary least squares regression in R. But if you look closely at these three completely different readouts, you will find the exact same metric anchoring all of them, the F-statistic. On the surface, this makes no sense. Comparing the volatility of two samples, testing the averages of multiple groups, and evaluating the predictive fit of a machine learning model are completely different tasks. Except mathematically they aren't. They are the exact same test, driven by a single engine. Every single time you see an F-statistic, the software is just running this calculation, dividing one variance estimate by another. The numerator represents the variance you actually care about, the active signal you're trying to measure. The denominator represents the baseline random noise in your data. Once you understand how this simple ratio behaves, the F-statistic stops being a black box number on a screen. It becomes a clear, logical tool you can use to prove exactly what your data is doing. To understand the F-test, we have to look at what happens when a real signal cuts through the background noise. If both variance estimates in our equation are just measuring the same random ambient variability, their ratio will hover right around 1. You are dividing noise by noise. This chart shows the F distribution. If we map out all the probable outcomes of that ratio, we get this curve. Notice that it peaks steeply near 1. You'll also see it has a hard stop at 0. Because variances are calculated using squared deviations, a variance can never be negative. Therefore, a ratio of two variances cannot be negative either, but the distribution stretches out into a long right tail. When the numerator contains a genuine signal, it outpaces the noise in the denominator, pushing the ratio far above 1. That right tail is where statistical significance lives. Unlike simpler distributions, the F distribution requires two separate parameters to define its shape, one for the degrees of freedom in the numerator and one for the denominator. As your sample size grows and the denominator's degrees of freedom approach infinity, the denominator's variance estimate becomes exact. At that point, the F distribution converges into a scaled chi-square distribution. This bounded, skewed probability map is the universal scale we use to evaluate our three analytical tasks. We begin with the most literal application of the ratio, comparing the volatility of two independent groups directly. Imagine you want to know if daily sales at two retail branches share the same underlying volatility. Analysts often run this check before deciding whether to use a pooled or Welch's t-test for comparing averages. This visual shows our sample data. Branch A has 25 days of data and a standard deviation of 1,800 rupees. Branch B has 22 days of data and a standard deviation of 1,100 rupees. To test if they are equal, we square those standard deviations to get the variances and divide them. By convention, we place the larger variance in the numerator. That math gives us an F-statistic of 2.68. To see if that is significant, we check an F-table. We find the column for the numerator's degrees of freedom, 24, and the row for the denominator's degrees of freedom, 21. The intersection sets our critical threshold at 2.37. Our calculated ratio of 2.68 clears that threshold. The signal beats the noise, meaning branch A's sales are definitively more volatile. In modern practice, this specific test is highly sensitive to non-normal data. If your data isn't perfectly bell-shaped, this test will trigger false positives, which is why analysts often prefer Levine's test or skip straight to a Welch's t-test. Direct variance testing is useful operationally, but the true power of this mathematical mechanic is that it allows us to compare group averages. When multiple groups are running side by side, we need a way to detect if one of them breaks the pattern.
This brings us to the analysis of variance, or ANOVA. To determine if the average values of three or more groups differ, we don't actually evaluate their averages directly. We analyze their variance. This chart is a standard ANOVA summary table, structured here for a factory tracking defect rates across 4 production lines. The numerator of our F ratio here is the mean square between. It measures how far the individual line averages drift away from the grand average of the entire factory. The denominator is the mean square within. It measures the natural random spread of individual data points inside their own respective production lines. If all 4 factory lines share the exact same true defect rate, the variance between the groups is just the exact same random noise we see within the groups. Divide them, and the ratio is roughly 1. But in our factory data, the between-group variance is 16.2, and the within-group variance is 3.0. Dividing those gives us an F-statistic of 5.4. Our F-table tells us the critical value for this sample size is 2.87. Since 5.4 is larger, we know for a fact that at least one factory line has a statistically different average defect rate. However, ANOVA is an omnibus test. It tells you that a difference exists somewhere, but it won't tell you which specific line is malfunctioning. You need a post hoc test, like Tukey's HSD, to isolate the exact source. By dividing total variance into between and within categories, ANOVA lets us test multiple groups at once without inflating our false positive rate, all relying on the exact same F-ratio logic. We apply that exact same logic to predictive modeling. When you build a complex algorithm, you have to prove that it actually works. To do that, your regression model, taken as a whole, must demonstrate that it is better at predicting outcomes than just guessing the historical average for every new data point. We use our F-ratio again, but we swap the terminology. The between-group variance becomes the variance your model successfully explains. The within-group noise becomes the unexplained variance, or the residuals. Consider a model predicting loan defaults using 4 variables across 500 accounts. The model has an R-squared of 0.18, meaning it explains 18% of the total variance. We divide that 18% explained variance by its degrees of freedom, and divide the remaining 82% unexplained variance by its degrees of freedom. This yields an F-statistic of 27.2. The critical threshold for these parameters is 2.39. We easily clear it, proving the model is statistically significant. Note the distinction here between significance and effect size. The high F-statistic proves the model is definitively better than random guessing. The low R-squared of 0.18 proves its practical predictive power is still quite weak. Even at the bottom of a machine learning output, the F-statistic is simply doing what it always does, proving that the signal your model extracted overpowers the background noise. Whether testing direct variance, ANOVA, or regression, you're looking at the exact same mathematical concept. Strip away the situational notation, degrees of freedom, and sample sizes, and one question remains. Is the signal divided by the noise greater than 1? You must interpret this result carefully. An F-statistic confirms that a signal exists. It does not mean the signal is practically useful for your business. It is an alarm bell telling you that your groups differ or your model works, but it will never hand you the specific source of that difference. The F-test gives you permission to keep looking. You must pair it with follow-up tools like Tukey's HSD or R-squared to extract actionable findings from your data. When R.A. Fisher developed this underlying theory a century ago, he provided a way to standardize our search for meaning. The elegance of his design is its scalability. The exact same ratio that compares the volatility of 2 small samples scales perfectly to evaluate massive predictive algorithms. The F-test is the foundational mathematical architecture that allows us to separate truth from randomness.